We're going to begin with this problem, which is very similar to the one that we did on Friday at the end of class. We've got a 25 kilogram chair initially at rest on a horizontal floor. It requires 365 newtons horizontal force to set it in motion. Once the chair is in motion, it takes 327 newtons force to keep it moving with constant velocity. We want to find the coefficient of static friction. Coefficient of static friction is going to be represented by the symbol mu s, and although I will not always write this, I want to make a point that this is a maximum value. Okay, because remember, the coefficient of static friction can change. So it changes until the object actually begins sliding up to a maximum peak. So we're going to solve for that peak amount, and then coefficient of kinetic friction we would call mu k. Okay, so we have some information. We've got a mass of the chair equal to 25 kilograms. We've got a horizontal force. I'm just going to say force applied is equal to 365 newtons to set it in motion, and then once it begins moving, then we've got force applied becomes 327. Okay, so we want to find the coefficient of static friction first. The coefficient of static friction is equal to mu k, and we would say that mu k is equal to the force of friction, which I'm going to abbreviate F sub F, over the normal force, which would be F. We'll call that F sub n. Now, at this point, I think we should be able to start abbreviating forces. Most of you are already doing that anyway, but instead of all the agent-object notation, I think it's important to do that. But once you get to the point that you know what the agent is and what the object is, you should be able to start abbreviating. But it is important as you start labeling forces, or as you start dealing with them on the force diagrams, that you make sure that you know where the force is coming from and what it's being applied to. So to be able to solve for mu k, we need these two values. And again, I should say, I said mu k, but I really, which I could do first, we've got the information for it, but I actually wanted to do that as a mu static first. And again, we are doing that as static friction max. Okay, so let's construct a force diagram first. And right there. Okay, we've got a 25 kilogram chair, so we know we have some mass. And because we've got mass, we know we have weight. We're going to have a normal force, which is going to be the same quantity, because it's going to accelerate across the floor horizontally. It's going to take 327 newtons to keep it moving. 365. So we're going to have let me actually lower the size of these slightly so that I can stay within the room I have on the problem. I'm going to drop this back to about there, and drop this one back to about there. Okay. And then we've got the 365 Newton force to the right. Doesn't have to be to the right, but we're going to make it to the right. And at the point that the object breaks free, what can we say about the friction force compared to this force? In other words, we're applying this force, and the friction force is building until eventually it breaks free. At that point, we should be able to say that this force is the same. So we've got, let's label them. This is the normal force. This is force of gravity, which I'm going to keep as Earth on object. This is the force applied, which we know is 365 newtons. So this is going to be a negative 365 newtons. And what would we call that? That would be the force of friction. All right, and our earth on object is going to be 25 kilograms times negative 9.8. I can't get my decimal in there. There it is, sort of. And how much is it? Negative 245. So what's the normal force? Positive 245 newtons. Okay, so we can say at this point we've got all the information that we need, that the mu s max equals the friction force of 365 divided by the normal force of 245. Take the absolute value of that because mu is a positive value. And what do you end up with? 1.49. No unit. All right, so how would we go about getting the coefficient of kinetic friction? Yeah, all we're doing is changing the friction force, which is 327, divided by 245. Again, this is negative. I'm not really concerned about whether or not you put the negative in these cases because it's going to end up absolute value anyway. And do we have an answer for that one? Okay. And no unit again. In this case, we've got a box of books pulled down the hall by a student, and they're pulling on a rope attached to the box. And the student pulls with a force of 185 newtons directed at a 25-degree angle with respect to the horizontal. The box has a mass of 35 kilograms. The coefficient of kinetic friction between the box and the floor is 0.27. Find the acceleration. Okay, so let's start by finding all the forces that are at work here. So let's start with the force diagram. Okay, so there's our box of books. We've got the student pulling with 185 newtons at a 25-degree angle. So we're not trying to sketch these from the standpoint of being, you can if you want to, but we're just trying to get an idea here. So we've got 185 newtons at 25 degrees. And let's put in, well, I'll draw the angle in a moment, but we know that this is the force of person, or an applied force would be fine on books. And what else do we have? We've got a weight. We know that we have a box that it has 35 kilograms worth of mass, so we can construct a downward vector.
That's 180, right?
185, yes. Okay, and this is going to be m times g, the force of gravity, which is going to be 35 kilograms multiplied by negative 9.8. And let's see, I've got that as negative 393 newtons. Check me on that though. 243? 343? Okay, so this is then 343. Okay. What else do we have? We've got a normal force. You're correct. But the normal force isn't necessarily going to be the same as the weight in this case. I'm going to take it there for right now, because we also have our components of the pull for like this. So we actually have an extra force in the y dimension that we have to be concerned with. We also have one other force, which is friction. We have kinetic friction, so I'm going to put a value there. We may have to resize some of these to make them realistic, but for right now, actually I can resize that one right now, because there's only one other force in the x, which is this one, so it's going to have to be the same size. Looks like about there. All right, so this angle is a 25-degree angle. All right, and we can say that this is force pull on books in the x. This is force, I'm out of room over here, so I'm just going to say force in the y. That's the pull on the books in the y. This is the normal force. And this is force of friction. Okay. All right, so from a sum of forces, we know that the sum of forces in the y dimension equals what? Think about it. It would be 0. Why would it be 0? No, they don't. They do not cancel out, because that wouldn't. We've got this component of the pull as well. It is being pulled up, but it's not actually leaving the surface. It's still being dragged down the hallway. So what direction is it accelerating? Accelerating down the hallway horizontally. It's not accelerating up into the air above the hallway. So we can say that it's constant velocity in that dimension. So that would be 0 newtons. And that would equal, for summing forces, we've got force surface perpendicular to books, plus we've got force pull on books in the y, plus we've got force earth on books. Okay, so we've got 3 forces in the y. Why do we need to go through summing this, you think? Well, what is it that we're trying to find? We're trying to find the acceleration, and to find the acceleration, we've got a coefficient of friction here. We are going to need to know something about this this friction force eventually. So we're actually going to solve for this force, which we don't know. Okay, we know this one, and we know this one, and we can get this one. So sum of forces in the y is equal to force, equal to 0 again. And that equals F surface perpendicular to book plus, what would we write for this? So it would be sine of 25 degrees times 185. Plus, this would be the same as mg, but we've already found that as negative 343. So if we're going to solve for the net force, we have to do a sum of forces in the x. And that sum of forces in the x is equal to F net. And that equals m times a, which is equal to force of, raise this back up just slightly, force of the person, the book, in the x, plus the force of friction. Okay. So we can say that acceleration is equal to what? Force person on box in the x plus force of friction divided by what? Divided by m. Good. All right, now how can we write, come over here and give myself a little more room. How can we rewrite this the force of person on books in the X using the diagram. Cosine of 25 times 185. So we've got, for this one, cosine 25 degrees times 185. Yeah. I don't need to know that number yet. Plus force of friction. Where do we get the force of friction? Okay. So I'll pause this for a second and give myself some more room.
The amount of force pulling over the normal force is the coefficient of friction. We don't know what's pulling, but
we know what's pulling,
and we
but is the pulling force exactly opposite of the,
no, we
of
need
the friction force?
X direction.
Right. It can't be the same. If it was the same, it wouldn't be accelerating. So we can say that force of friction is equal to mu k in this case, because it is moving, I believe. Let's check to make sure.
Should be.
Yep, it is moving. So we've got mu k times the force normal. So we can say that this is equal to mu k, which was 20.27, times the normal force, which we found right here, 264. Because that's the definition of the force of friction from the viewpoint of the coefficient of friction. So force of friction is equal to the coefficient of friction times the normal force. So this is our normal force. Okay?
And then that's all over.
And then that's all over the mass, which was, what was the mass again? 35? Okay. So again, what this value is right here is mu times the normal force.
Yeah, but I don't know why you're getting excited about it. It was a good meeting. It was a good idea. There's no need to get excited. Oh no, I see the interview on motion.
Okay, so our next problem is a 75 kilogram box slides down a 25-degree ramp with an acceleration of 3.6 meters per second squared. So we're given an acceleration this time. If we're given an acceleration, of course, that allows us to find a net force also. We want to find the coefficient of kinetic friction between the box and the ramp. Okay, so usually with most of these problems, you're going to start out by trying to resolve all the forces, find out what they all are. So if we were to construct, if I'm going to resize this, okay, so I'm going to construct a ramp. Okay, so we've got our ramp. We're at 25 degrees, so I'll go ahead and put that in here. All right, we have a box on the ramp. I'm just going to represent the box as a point. And we want to resolve as many of the forces as we can. We know that it's 75 kilograms. So as we start to draw forces, we can say that we've got 75 kilograms worth of mass there that's going to be converted into a weight. We need the components of that weight, which are going to be here and here. Remember that you're making one of the legs of the triangle parallel to the ramp itself, and you're making the other leg of the triangle perpendicular. We're going to have a normal force draw with this. Going up into my problem for that. But I can move the problem in a moment. And what else do we have? We've got a friction force up the ramp of some value. And I think that's all the forces. Okay. So let me write down this number and then I'll remove the problem so I'm not working in the middle of it. All right, so we've got acceleration equal to 3.6 meters per second squared, mass equal to 75 kilograms. And we're looking for the coefficient of kinetic friction. So we're looking for mu K. Okay, first of all, we've got this particular one is force earth on crate. We can say that force earth on crate equals m times g, which is 75 kilograms multiplied by negative 9.8 meters per second squared. So force earth on crate is equal to negative 735 newtons. Okay. We have theta is here at 25 degrees. Got the same theta here with a similar triangle. This side then is going to be force earth on crate in the y, force earth on crate in the x. So the earth on crate in the y is going to be the cosine 25 degrees times negative 735. And I'm getting a very beastly number. That's what I got. I probably tried to round that up, but I think it actually stays right there. And then I've got earth on the crate in the x, and that became, that would be sine of 25 times negative 735 newtons, and that was negative 310. Check me on these numbers, please. 311, okay. I can go with that. Negative 311 newtons. Okay. So, all right. How about the normal force? Think about the motion. Can we set that as 0 in the y dimension as a net force? Yes, because it's sliding down the ramp, so, or moving up the ramp, whichever way it happens to be going. So that would be positive 666. At least it's positive.
666. Wow.
And how about this force?
I think you did that on purpose.
Can we say that the force up the ramp is equal to the force down the ramp? No, because we've got an acceleration. So this force, which we'll call F friction, is equal to, how are we going to find that?
The thing we used last time.
Okay, we're going to have to sum some
Force
forces,
of friction equals mu.
but we don't have mu. Okay, so what we're going to have to do to get the force of friction, we need to sum the forces. To get that, the force of friction is going to be one of the components of the sum of forces, so that would be an unknown. We can't have an unknown if we don't know the net force, so that would give us two unknowns. So, but we can find the net force because we know mass was how much? 75 kilograms. And we do know the acceleration of 3.6 meters per second squared. So that's going to be equal to how much? 270 is correct. Thank you, Chen, for the scientific notation. So now we have F net is equal to this, MA, but F net is also equal to force of friction plus force earth on crate in the X. So now we have 270 newtons. We're going to have to watch signs on this. I'm going to write it out first, though. 270 newtons is equal to force of friction plus negative 311. Does the problem say anything about direction? Sliding down. Okay, I'm defining, and the way I've set this up is, and this actually follows from from gravity being negative. I'm setting this is my negative, this is my positive end of the ramp. So that means that this 270 is negative. So the force of friction is equal to a positive 40.
41.
It is 41. I was using 310. So 41 newtons. Okay, so we just found that one. Now, what we're looking for is the coefficient of kinetic friction. Coefficient of kinetic friction, after going through all of that, the solution to the problem is the easy part. Coefficient of kinetic friction equals to friction force divided by normal force. So we've got 41 newtons divided by positive 666.
It's positive.
Yeah, I'm trying to make it more positive than it might be. And
At least it's up the bottom.
that's right. 41 overtakes the beast. So what do we have? I had 0.13, but I used 310. How much? 0.06. Oh, but hold on.
Was your calculator in radians?
No. And no unit, of course, kinetic friction. Okay. Questions? Gavin? Questions? Chen, you're being recorded. Okay, so you don't like Alex. Ryan, who has a puny mass of 81 kilograms, starts at rest from the top of a water slide.
I'm at a water slide park.
Angled at, no, didn't say you were at a water slide park. This is probably your backyard with a slide, and you've sprayed some water on it. Okay? That's the best you could do, right?
That's the best.
Okay, so we've got a mass of 81 kilograms, starts from rest, the top of a water slide, angled at 42 degrees to the ground. He exits the slide at the bottom 3 seconds later, going 15 meters per second. What's the coefficient of kinetic friction between Alex and the slide?
You mean
All
Ryan?
right.
It's Brian.
Yes. Okay, so some information that we've got. We've got mass equals 81 kilograms. We've got a theta of 42 degrees. And we've got a mu that we're looking for, and that's specifically mu k. We also have some kinematic data. We've got VI is 0, starting from rest at the top of the slide. We've got a VF of 15, and we have a delta T. What was it, 3 seconds?
Yeah.
All right, so from the kinematic data, we should be able to find acceleration. Okay, so we've got VF, VI, delta T. We can use VF equals A delta T times, or plus VI, excuse me. Say it again. Yeah, so there may be another equation we can use, but this is probably the simplest.
Number 3.
So we've got VF minus VI divided by delta T equals A. VF is 15 minus 0 meters per second divided by delta T of 3 seconds. So that works out easily to acceleration. We can add this up here. Is 5 meters per second squared. All right. What next? Keep in mind what we're shooting for. We're looking for coefficient of kinetic friction that's going to equal the friction force divided by the normal force. So we have to have ourselves a friction force and a normal force. So I've got as my next step in doing this problem that I'm finding the net force along the slide. Okay, because we know that there is a net force along the slide. So we've got F net equals MA, and that is Ryan's mass of 81 kilograms multiplied by our acceleration of 5 meters per second squared. And we've got 405 newtons. Okay. Now that we've got that, we can say that F net is the sum of forces, which we know is 405 newtons, and it's down the ramp. And that's going to equal some forces. So let's think about those forces. One thing that we have not done is draw a force diagram. So we've got, let me sketch in my ramp. So we've got our X and Y axis. Okay, so we've got our slide, which is really just a ramp. We've got an angle. Do we have an angle? 42 degrees. We do. So 42 degrees. We've got, here's Ryan, also known as by his friends as the blue dot. And we have his weight. We have components of that, which would include this. And I need.
It makes you feel better when you say all these kilograms.
Okay, so we've got this theta. We have. I'm just going to write theta there to avoid taking up too much space. It's still 42 degrees. We've got the weight, which I'm trying to see if I've actually got that worked out in newtons. Okay, so I do not. So let's go ahead and calculate some of these forces. Let me finish drawing though. I also have a normal force, and I've got a friction force. I'm drawing the friction force as less than the force of the weight force down the force of Earth on Ryan down the ramp, because I know that he's accelerating down the ramp. These two forces should be approximately the same. Okay, so net force is going to equal what two forces? Let's think about that for a moment. Force of friction here, and this is force Earth on Ryan in the X dimension. So that's going to be our sum of forces equation. Force of friction plus force Earth on Ryan in the X. All right. So negative 405 newtons equals. Can we get the force of friction immediately? Do we know that now? Do we have enough information to calculate it right now before we do something else? So in other words, can we look at the diagram and get the force of friction? How about the x dimension of weight? We can get that because we know that this is going to be the sine of 25 degrees. Oh, sorry, it's not 25 degrees anymore. It's 42 degrees. Times the weight, which is m times g. Okay, and then that's going to be plus the force of friction. So negative 405 newtons equals sine 42 times the mass was 81 kilograms times negative 9.8.
Equals 793.
Okay, so this component does this part or the whole thing?
Oh, no, just the component.
Okay. So say it one more time, negative 7.
That's just yeah, 793.
531. Okay, don't forget to take this. The sine of 42 is 0.67 times 81 times negative 9.8. So that would be newtons. That's just this side. That's not the weight. Plus force of friction. So force of friction becomes 405. And that is going to be a negative 126. Yeah, I have a sign reversal. Whoa. 405. So that should be a positive 126. Okay, so we've got 126 newtons up the ramp. All right. So again, focus on what we're looking at. We've got normal force and friction force. We've got friction force. That's the negative 126. So how are we going to get the normal force? It would be the positive of the y component of the weight. So yes, it is positive. Did I put a negative in again? Yeah, thank you. Positive 120. It'll be absolute value in the end anyway, but it is positive. And this side of the triangle, which is going to be this component and the normal force will be equal. This would be the cosine of 25 degrees. I still want to do 25. Where did that come from? The last problem? Cosine of 42 degrees times 81 kilograms times negative 9.8. So this is negative 590 newtons. Okay, do I leave a negative there? Because it's actually this value, which is going to be equivalent in magnitude, opposite in direction. So now I've got positive 126 over positive 590. 0.21. And that would be the final answer. And let's go back and check the problem to make sure that's what we're looking for. What is the coefficient of kinetic friction? So that is what we're looking for, 0.21.